I want to start from this position of the video. Here's your reinforcement. Bottom of this, none up here, as reported by the person that posted the video. None here either. I'm sorry, this is the flip side of this. None presented here either. This zone here. None there. What it looks like is where the reinforcement might have been here and here. This may look like it's a wooded area. Can't prove that. Noteworthy, here's the table it's on. This is a pivoting point. It can pivot like that on its axis. Well, you'll see it down here at one point. You'll notice it's down here. Another point, it's up like that. Kinetic energy is what's going on here. That this deflection takes place, and so much kinetic energy is built up in that steel. And that steel and this steel that's right there, that it has a connection, a bond with the concrete. And so in deflection, the bond strength, and here's the reinforcement between it, is green. And I'm showing top and bottom cover, top cover type thing. The bond strength, the deflection, the loading comes down here, causing this zone here to deflect. And that zone would look like, I'm going to go like that. And here's our last piece here. Okay, you can put that back in there if you want. I'm going to remove that part. There's our deflection here. Pivot point right there. So we got our loading here. Our pivot point here. Pivot point here. There. All right, so think of this as the FIU bridge now. I'm going to put it in there. I'm going to draw it in. I'm just going to do these uprights. And this is the wrong location for that. Let's clear that out. Let's start over. Okay. So FIU bridge. And like this. Okay. This is nodal area 9, 10. That's 12, 11, 9, 10. So this is nodal area 9, 10. This is 11 and 12. So here's our 8 and 9. This is 9. I'm screwing this up. Hold on, guys. Let's just go backward. That's 12, 11, 10, 9, 8. Okay, 9, 10's down the bottom. This is 9 coming down. That's 10. And over here is 11, 12. 11, 12 nodal area where the two of them meet. I'm going to remove those now. This will be 10, 11 nodal area. This is where they two meet up there. This is number 11. This is number 10. And that was the eraser. This makes it easier. So do that again. So that's your 12. That's your 11. This is 11, 10 nodal area. This is your number 9. That's your 8. So this is 9, 8 nodal area where they meet. This is 9, 10. Nodal area. 9, 10. Yeah. 9, 10's down here. It's 10, 11. 10, 11 nodal area. Okay, blister bars up here. Now, the loading is here with this ram. But the dead load of this structure of the... Oh, shoot. I got to answer this phone call. Okay, so just like this sample here, the dead load of the structure, the post-tensioning, elongating, that they had in there, the post-tensioning, elongating, they used to hold the structure together. Elongating, think of it as a steel, was able to stay rigid to this nodal point here that was created. Nodal point midsection. Interesting enough, static says, always take your load points at your nodal areas. At your nodal areas where you'll do evaluation. Well, that was that might work still. I mean, if you say, okay, over here we got a, 800 tons, and then this one is 850, and out here you're back to 900. Well, just before there, I don't know. It wouldn't be the full value. I'm just giving you something. 900 tons. I'm just showing you. Well, from here to here to here, you say what, another 100? No, you split the difference, so this is what? 850? No, because in theory, this is not supposed to be taking any load like that because, there's a because part, because the loads follow this path, theoretically. So we're following that path, locked in, following this path here. And this would be more like a tension path. But if it can't take the tension, the load on it, it fractures. It fractures. And this example we're showing here with this loading here, it will fracture. Hopefully I didn't overstep my bounds there with how I was doing that. Sometimes, I'm supposed to do it live, I make mistakes sometimes. That the tension in here fractures. This is where we get that collapse, where if you look at it, you'll find this collapse with the video camera of the FIU bridge collapse. You see the deflection here. Let's see, let's do that. Before we do that, let's go ahead and let's get this video going, and you'll see it break again. And here we go.
If we slow down the footage, here is that failure again. Look how... Now remember, this is a beam in which we have left out the shear reinforcement, and this is the consequence.
One more time.
If we slow down the footage, here is that failure again. Look how sudden it is.
Well, it was the kinetic energy built up in that steel. Kinetic energy built up in that steel. There's your shear plane right there, and the steel here. That it's trying to hold that bond I spoke of, I told you about, and the fracture happens there, is where it breaks apart. We first see with our eyes here. This is where we see it. But at that point, this tension is so great in here, and you can see the load path here, in this case more clearly there, that we're looking at it. That so much tension between the rebar and the concrete that we're seeing the break failure of it. This section. All right, let me back it up and do that again for you.
If we slow down the footage, here is that failure again.
What I want you to note in this one is this. Look at these guys. Look at the direction of them. Look at the direction of it. When the load is released, that is, the break happens, and the load is released, it tells us true path of the kinetic energy, the bow and arrow. It tells its true path of the kinetic energy. It's right here. Straight up and down. With the load cell, which is part of Newton's equal and opposite reaction, right? Force is going down, and when it breaks free, the energy is in that direction, even off the top of these fibers here, off this concrete here, presentedly. And you see what's happening there. Those are your directions, your fibers. So now let me get you the other one. I'm trying to double dip in this video. Give you this one, and also FIU bridge. So I want you to see this is just a bond break that just happened abruptly. Abruptly, very abruptly. Brittle fracture, if you will, but not really, because there's a bond break here between this section here happened. Let me go with my orange. There's a bond break, orangish color, that happens between this section and this section. And that bond break is your reinforcement in here under tension. Under tension with the deflection taking place right there. So it's trying, this force over here is pushing down, and it can't make it out to here where they placed the location. If they'd have put that force over here, of course it would have been 1-to-1 just crushing. But they placed it such, strategically such, that we're back at this position where this happens this way. You move this load cell over here, you might get breaking back here. This might make it over to there. Don't be confused with the. Don't be confused by leaving out the kinetic energy is built up. The bond is built up. That you're looking at this bond break here. This is the bond break right here. This is your bond break. All right, this is it. You're looking at it. Right here. This section breaks apart from the rebar itself creating a plane, a shear plane by it having its, say there's two bars in there, we're looking at the top view, if you will. And the reinforcements there. But it's got to hold the concrete together. I mean, the concrete's got to bond around it. And when that force is applied, it breaks apart. That kinetic energy is there, and you get your boomerang, your arrow, your direction, your released energy, your kinetic energy is here, shown in this direction with these little fibers. Let me get you now the bridge. Now I want you to overlay the load cell, the dead load of the structure. The dead load of the structure. Just the weight of it, right? The load of it. Over here, when it comes down here, it's pretty much right down this column, load right down to the base, right, the piers. All right, same thing with this one. All right, so this is your number 12. This is your number 11. This is your number 10. This is 9. All right, so that's that nodal area 9, 10. That's where the two of them meet. This would be 11, 10 where they meet. Okay, and this will be your concrete, your post-tensioning. Your post-tensioning, keeping this whole thing taut. It's really cranked up, right? It's really, put a little spring in there for you. It's really taut, so if this tries to, this can't bend down, so this can't deflect. I'm saying it can't, it did. It can't bend down because this is so taut, this reinforcement, that it won't allow it. You try to grab it with your hand, grab this with your hand, right, and try to pull it down. You can't, because it's so, the thousands of kips that are in here are so tight that you just can't pull on it. It's like a tight wire, a tight garden cable for your laundry. And it's so tight you can't pull down on it. And these are immovable. These points here are immovable. It's not quite anchored down to here, so I don't want you to see it that way. But it's compressed. It's in a concrete core, if you will, a column of concrete. And this is so taut that you can't pull down on it. Now let me back that out. So now putting it back for you. This is your 9, 10, remember? And right here is where your fracture is going to happen. Just like I showed you with that load. Now let's go back. So here's the load. That's the dead load of the structure, the span. The span is your dead load. And why, if the look, I even do that in real life. I put L L-A-O-D. I don't know if you guys can see that, but I know that's what I did. I did L-A-O-D. Even in real life, I do that. I do that. Anyway, so dead load is the oh yeah, and so so the theory is that this has worked as a truss system, not my theory, and that this slid out. That the weight of this slid, pushing this number 11 and pushed number 12 off, and that caused a collapse. Well, the design of this is such that the base was how this thing worked, and this was not. This was just a canopy, just an umbrella. This is the profile of it like this. That's number 12 at the end here, right there. So it's just a canopy. This is the diaphragm. It's huge, it's like 4 foot tall here at the end. Right here, 4 foot. Not the column. This is the deck now. These are huge, different dimensions on that end. On this end, it's approximately 4 feet, and they use post-tensioning here, down here, to hold the structure together. And they had some post-tensioning up here too to keep the canopy from flapping over. And this is the side profile of it. It's like an I-beam is what the engineer's intent was talking about. And that this was just a it was supposed to work in tension. The bottom plate was just supposed to be basically lay waste to it. Put what you want on top of it, to a limit, of course. So now we have the load there. So now let's go ahead and run this with the accident. And right here, I want you to observe it. It's dead load. DL, right? Right there. See the brake? And there's your brake. All this is intact. There's your dead load. The weight of the structure. There's a man that's grade. You act like that, like you saw the fibers. He's going to stay there, and this is going to come down. Ultimately, the cable will grab him. There's a lifeline cable here, safety cable. And let's go back there. Okay, so I want you to see that what you're just looking at. And this is cable in here, so it can't eject off. It can't eject off like it normally would. There's cabling here. But what do we look like we have here? What do we look like we have there? This is where they said this slid off. This was already fractured all to hell. That's in previous videos of mine. You guys want to see that? I can show you, go back over that. But this, I just want to give you a different rendering, if you will, of what you're looking at when you see this fracture. With some dynamics in it. The cabling is going to act differently. The connections will be differently. But this is what you're looking at. Now let's go ahead and let that play. I won't let it, well, no reason to let it play. I can drag it. Hold on. Okay, so there's your brake. There's your brake already. From the dead load of the structure and what I believe the post-tensioning acting like a bar, failing right where you see it failed. They have it initially starting here, sliding off. The video does not show that. They say, well, you see some ejection. All right. Well, this can't move. This can't extend. This bar, these guys were just putting post-tensioning in this bar. This can't extend with a bar in it. It'll make itself longer. It can't do that. And there's a nodal down there anyway, some steel there. This is just bad on, this is NTSB that did this one. And they've held me up on my FOIA request for now 2 years. Of course, with the C word coming in, that was probably a good excuse for them not being in office. But first they said we released it, and here it is, and they gave me files I couldn't open. So I still have the files, but I can't open them. They weren't able to, you can't download them. You've got to be able to access them. And of course now those files have expired. And there's no one in office to speak about it. Of course I've written them. Okay. So this is what their claim is. Clearly the imagery shows break here. You may see some as this goes down, a little scatter of material. But this is more is what you see. And what would cause that sliding effect? These are all locked in. These are all locked. They're not moving. They're locked in position. Why would it slide there? Unless you get this deflection first. Then you can compress it and pushing this out and causing this fracture, this rotation, etc. But no,